In the previous video, we configured the drive to manually control the spindle from the drive keypad, and we added a switch to tell the drive to accept commands remotely from the CNC instead of the local keypad. By the end of this video, we'll be able to control the drive remotely from the CNC using Modbus RTU over an RS485 network. This is everything you need to do to get an Altmill CNC router using an SLB EXT controller to communicate with a WEG CFW320 Series drive. If you're already familiar with how to do all this stuff and just needed a list of what to do, take a screenshot of this slide and this schematic, stop the video, and go do it. For everyone else, stick around. I'll walk you through all of these steps and share some insights and tips so you can get the most out of your Altmill CNC router with a WEG CFW320 Series drive. Here we go. Now if you haven't done so already, turn on the drive and then power up the CNC. And don't forget to reset the Altmill Z-stop. Go ahead and switch to CNC control of the drive using the switch we added in the previous video. And leave it there for the rest of this video. We're going to start with configuring the drive for remote operation, and then set up the drive's communication parameters to match the Altmill defaults to keep things simple. Then we'll do the Altmill configuration, which, since this is an unsupported drive in this version of gSender, will be a bit involved, because we have to customize all of this stuff for the WEG drive. We'll add the RS485 wiring, something that should be simple, but always confuses folks because of the seemingly random labeling scheme. And finally, we'll do a test run or two, learn some troubleshooting techniques, and cover some loose ends and resources. Timestamps to each item on this list are included in the video's description if you just want to jump directly to a single topic. The terms drive, VFD, and variable frequency drive all mean the same thing and will be used interchangeably in this video. Now before we get started, why would we want to control the drive via Modbus RTU instead of the easier PWM method? Because with Modbus RTU, the CNC controller can tell the drive exactly what speed it needs to be at, and it can ask the drive via Modbus what the spindle is currently doing. With PWM, the controller can't specify the exact speed, it can only get close, and it can't ask the drive what the spindle's doing. So if you want reliable, predictable, accurate control over your drive, it's definitely worthwhile to take a few minutes to learn how to control the drive via Modbus RTU. Now it's a bit intimidating, because there's a whole bunch of little details you have to take into account, as you saw in the opening slide. And if things aren't set up correctly, it won't work. No worries though, because you now have this video that walks you through exactly how to do it right every time. Okay, let's configure the drive. In the previous video, we added a switch to tell the drive to accept commands remotely from the CNC instead of the keypad. But we never told the drive where those commands would come from. The drive can accept commands in multiple ways: Ethernet, Modbus RTU, analog inputs, digital inputs, etc. So we need to tell the drive we'll be using Modbus RTU on a serial bus for remote control of the spindle speed, run-stop commands, and the forward and reverse commands. In the manual, we see parameter 222 tells the drive where the spindle frequency or speed comes from when in remote mode. We want the frequency to come from the serial RS485 bus, so we need to enter a 9 into parameter 222. Parameter 226 tells the drive where the forward and reverse commands will come from when in remote mode. We want those also to come from the serial RS485 bus, so we enter a 5. If we need to invert the direction for some reason, we could enter a 6 instead. And parameter 227 tells the drive where the run-stop commands come from when in remote mode. We want those to also come from the RS485 serial bus, so we need to enter a 2 for that parameter. Now we need to tell the drive how the Altmill formats the bytes it sends to the drive, the serial protocol. Parameter 308 is the drive's address on the 485 network. gSender uses a default address of 2, so we'll use that. Parameter 310 is the baud rate. gSender defaults to 19.2K baud, so we'll use that. Parameter 311 tells the drive how the byte is formatted. gSender defaults to 8 bits, no parity, 1 stop bit, so we'll use that. Parameter 312 tells the drive how the serial bus is formatted. The WEG CFW320 drive serial port can be used for a number of different things. We want to be a Modbus slave, so we enter that one. Parameter 313 tells the drive what to do if there's a communications timeout error. We'll leave that at the default, but you can pick any of these you like. Parameter 314 is a watchdog timer. When you use Modbus RTU, the master controller pulls the drive at regular intervals. This watchdog parameter tells the drive how long it should wait before issuing a fault and doing whatever we told it to do in a previous parameter. The factory default of 0 disables the watchdog, which is fine for what we're doing. We're finished with all of this. This is a read-only parameter where we'll be able to see what the drive thinks we told it to do. We'll use that when we do our testing in a few minutes. Now we're going to work our way down this side. And again, the bad news is CNC Labs gSender version 1.5.7 doesn't support the WEG CFW320 Series drives. So we're going to have to do a deep dive to figure out all this stuff. Bring up gSender and connect to the Altmill CNC. Go to Config, Spindle Laser. I like to enable this guy so I can manually control the spindle from the main carving screen. Apply that, then go back to the main screen, and sure enough, down here we can now manually control the spindle. Now we're not ready to do that yet, so let's go back to Settings, Spindle Laser. Now anything highlighted in yellow, like this guy, is stuff we've changed from the default settings. We want the normal CNC function, not a laser or a lathe, so that default works. The on delay is used by the RS485 control method to decide if the spindle's working or not. The Altmill pulls the drive periodically for spindle speed via Modbus. If the spindle hasn't come up to speed within this amount of time, you'll get an alarm 14. Now that's a huge advantage of using Modbus for VFD control. The controller always knows what the spindle's doing. We'll leave this at the default, which is usually more than enough time to get the spindle up to speed. The min speed just tells the controller not to allow speeds below this number. Now I don't have torque curves for this inexpensive spindle I got on Amazon, but usually a 2.2 kilowatt spindle's torque falls off rapidly at speeds below 6,000 to 8,000 RPM. Set this to whatever you want, just know that spindles are not designed to run at low speeds. At low speeds, the spindle will draw a lot more current and will be more likely to burn up if you push it too hard. We'll leave ours at the default 7,500 RPM. Max speed. We know this spindle is 24,000 RPM, so this default works. This version of gSender defaults to the CNC Labs VFD, which doesn't use RS485. How do we know it's not using RS485? Easy. If you look at the SLB controller, there are two LEDs right about here. The bottom one is green and it blinks each time the Altmill sends a command to the drive. The top one's red and it'll blink each time the drive sends a message to the Altmill. No blinky lights means no RS485. We'll use those LEDs to validate things in a minute. We will be changing this to generic Modbus VFD, but don't do it yet. We need to get it configured first. Scroll down to the Spindle Modbus section to do that. This is how close the spindle speed has to get to the requested speed within that on delay time we set earlier. 5% is fine. If it doesn't get within 5% of the requested speed within that on delay time, you'll get an alarm 14. We told the drive to expect 19.2K baud, so we'll leave this at the default. This has to match whatever you set the drive to. The Modbus receive timeout is how long the Altmill should wait for a reply from the drive before issuing an error. The default is 50 milliseconds. But what does that mean? Here's a scope trace of the RS485 traffic. This is the message going to the drive, and here's the drive's reply. Looks like the time it took to reply is well within the 50 milliseconds we're allowing. These first three are the drive's Modbus addresses that gSender needs to send the commands to. This is the address in the drive to send the run stop and forward and reverse control commands to. This is the address to send the spindle frequency or speed commands to. And this is the address to read to get the current spindle speed from the drive. Now on a lot of drives, figuring out what these addresses are can be a complicated exercise where you have to dig through the manual to figure it out, and even then still have to do some manipulation to get it to work. On the WEG drives, it's super easy because the Modbus memory address in the drive is simply the parameter number. So if we go look at the manual, we see parameter 682 is where we can view the drive's run stop and forward and reverse status. And when accessing the drive via serial comms, we can also control the drive with this parameter. Exactly what we want. So we simply enter parameter 682 for this guy. No looking up or manipulating special Modbus addressing needed. I love that. Parameter 683 is used to set the spindle speed. So we just enter parameter 683 as our set frequency Modbus address. To read the spindle's current speed, we want to use the same parameter 2 we used in the previous video to view the spindle speed in RPM. Okay, we told gSender where to send the speed, run stop, and direction commands. Now we need to tell it what commands to send. Looks like we need commands to tell the drive to run in a clockwise direction, counterclockwise direction, and a stop command. If we go back to parameter 682, it tells us everything we need to know. This is what each bit does. There's a better view of this in table 12.1. Bit 0 is called ramp enable. That means set this bit to start ramping up the speed. Clear the bit to ramp down. So that is our run stop control bit. Bit 1 is the drive's output. I just leave that enabled. If you clear this bit when stopping the spindle, for example, it cuts power to the drive's output, which means the spindle coasts to a stop and we have no control over it at all. It's just free spinning. If we leave this output enable set, then the spindle ramps down at the deceleration rate we specified in the previous video. Bit 2 is the forward reverse bit. We'll set this for a run clockwise command and clear it for the run counterclockwise command. We really don't care about the rest of these, so I won't spend any time on them here. Notice that this says it's a read-only parameter. The exception is, if you're talking to the drive via serial commands, which we are, then you can also write to this register. Let's rearrange that to make it easier to build our commands. We're going to be doing a lot of binary to decimal to hexadecimal conversion in this video, and I know everyone's not comfortable with that. Just know that each binary bit position has a value as shown here. For example, if we enable these two bits, we just sum their values to get the decimal equivalent. Also, most calculator apps have a programmer mode where if you type in a decimal number, it'll show you the binary and hexadecimal equivalents. Or you can enter a hexadecimal number and it'll convert to binary and decimal. Regardless, this video will assume you have some familiarity with binary and hexadecimal conversions. We need a stop command, a run clockwise command, and a run counterclockwise command. To run in a clockwise direction, or forward direction, we need to ramp up, enable the drive's output, and run in the forward direction. So we enter a 7 for that command. To run in a counterclockwise or reverse direction, we need to ramp up with the output enabled in the reverse direction. So we enter a 3 for that. To stop the drive, we just tell it to ramp down. Again, leave that output enable set so it doesn't shut down the output of the drive and let the spindle coast to a stop. We want to be able to control the spindle's deceleration. Forward reverse doesn't matter when decelerating, so I usually just set that to 0 to keep things clean. So that gives us a decimal 2. Now for the hard part. We have to figure out how the Altmill and the drive interpret the frequency or speed commands sent between the two. Every drive manufacturer seems to do it differently. The Altmill sends the speed in RPM as a 16-bit word. So when the Altmill wants the spindle at 24,000 RPM, it sends a 24,000. Easy, right? No, because the drive expects a 0 to 100% number, and since it uses 12 bits to do it, that value needs to range from 0 to 8191 plus a sign bit for a total of 13 bits. Now we're using the commands we created a minute ago to reverse the motor, so we can ignore the sign bit, leaving us with just the 12 bits of positive frequency values. So when the Altmill tells the drive to spin up to a maximum of 24,000 RPM, the drive needs to receive the maximum command of 8191, which in the basics video, we set to 24,000 RPM and 400 Hz in the drive. That means we need a scaling factor here to convert 24,000 to 8191. So 24,000 times what gives us 8191? Except since the count starts at 0, that's a total of 8192 steps, so that's what we're going to use in our math. And we get this. The 24,000 RPMs needs to be scaled down by roughly a third when talking to the drive. Now the Altmill can only handle 1 decimal place, so to get more accuracy, we'll multiply it by 10,000 and then divide by 10,000. So this is our multiplier and this is our divider, which go here as the multiplier and divider for the input to the drive. For the scaling factors for the output from the drive, coming back to the Altmill, we would just reverse the input scaling factors to scale the number back up to the 24,000 RPM the Altmill is expecting, right? Nope. Why not? Well, because when we read the speed from the drive, we're reading parameter 2, which is in RPM, not percent full scale. And remember, in the previous video, we divided it by 10 so it would fit on the 4-digit display. And we added a fake decimal point to make it appear to show thousands of RPMs. But that was just for show. At the end of the day, parameter 2 has 2400 in it when the spindle's running at 24,000 RPM. So when the Altmill reads the speed from the drive in parameter 2, it needs to multiply it by 10 to get it back to the 24,000 RPM range, which means we need a 10 for the drive output multiplier and a 1 for the output divider. I'll show you how to verify all this scaling stuff is working correctly in the troubleshooting section later in this video. We'll also want to tweak it a bit because this isn't quite what we need. Well, that's enough to get us started, so let's do the wiring. The only wiring we need to do is to connect the 2-wire RS485 network. Everything else was done in the basic configuration video. Most folks struggle with this because while some manufacturers follow the RS485 standard, most don't. And it's left to you to figure out which one your system's using. So let's try and understand this so we can make the right choice. It's important to understand that RS485 takes a series of digital pulses and sends 2 copies down the wires. One's an exact copy of your original digital pulses, and one is an inverted copy. The idea being, any noise that gets on one line will also get on the other, so the receiver simply subtracts the 2 signals. The noise cancels, and since one of the signals was inverted, the signal doubles. I grabbed a scope trace of my Altmill's RS485. This is the plus signal, this is the inverted or minus signal, and this is the difference between the 2 signals. Look how much noise that simple subtraction eliminates. That's called common mode noise rejection. It's rejecting noise that's common to both wires. Because of that, RS485 can reliably communicate well over 1,200 meters, or roughly 4,000 feet. Yeah, it's pretty incredible how reliable RS485 is. The main thing to remember is there's a positive wire and an inverted or minus wire, and you always connect the positive to the positive and the minus to the minus. If you add more devices, the same rules apply. The Altmill's SLB EXT controller gives us 2 ways to wire RS485. On the upper left corner of the controller, you can use this 6-pin RJ connector or this green Euroblock or Phoenix connector if you prefer discrete wiring. According to the schematic, pin 3 on the RJ connector is the minus or B signal, and pin 4 is the plus or A signal. Keep in mind, the RJ connector is labeled like this, so pin 3 is physically below pin 4. You can get pre-made cables to plug into the RJ connector from Amazon, or just get one from an old thrift store phone. It might have 2 pins populated, 4 pins populated, or even all 6 pins. Just make sure the center 2 pins are wired. Those are the only 2 you need for RS485 on this board. If you want to use the green Euroblock connector, you only need the A and the B signals. A is plus and B is minus on this board, which is common practice. Just beware, the actual RS485 spec says A is the minus and B is the plus. So you have to be real careful when setting up your RS485 system and know that these inconsistencies just confuse everything. I usually ignore the A-B stuff and just focus on the plus and the minus designations. That's really all you need. If I orient the cable's RJ connector like it's going into the Altmill controller and zoom in, I can see the wire colors. In particular, the plus wire on pin 4 is green and the minus wire on pin 3 is red. The CFW320 series of drives don't have RS485 built in, so you'll need an RS485 expansion module which plugs in here. I prefer to add the wires before plugging the module in, especially since my drive is already mounted and getting up under the module to insert the wires is difficult. just connect the RS485 plus wire, which we just figured out was the green wire, to the plus terminal, and the red or minus wire to the minus terminal. Again, in RS485 you always connect plus to plus and minus to minus. Notice that the WEG's drive do use the RS485 standard, where B is the plus signal. That's the opposite of how the SLB board is labeled, isn't it? So again, it's best to ignore the A and B labels and just connect plus to plus and minus to minus. With the drive powered down, remove the COM port expansion cover, plug the module in, and you're good to go. Apply power to the drive, and it looks happy. No errors, no faults. RS485 requires that you terminate the network with a resistor that matches the impedance of the cable at both the start and the end of the network. That's so energy doesn't get reflected back to the source and distort the waveform. The Altmill SLB EXT board has this built in. Do you need a termination resistor at the drive end? Not really. You only need a termination resistor for cables longer than about 20 to 30 meters. Now the folks at WEG are more conservative than that, and they say more than 3 meters. My drive's only about 12 inches from the controller, so the answer is no for me. But it doesn't hurt to have it in place, and the good news is the RS485 module gives you the ability to turn it on or off. So we'll set both of these switches to on, which enables the termination resistor. If you don't want the termination resistor, set both switches to off. The manual says any other combination is invalid, so make sure they're either both on or both off. That's because each switch is connecting one end of the resistor to the RS485 wires. This thing that looks like a USB port is not a USB port. Do not plug in a USB cable to this port. Notice that the module has a communications ground terminal. You don't want to use that here. It'll just create a potential ground loop that screws everything up. RS485 doesn't need a ground reference because we're comparing the signals to each other, not a ground reference. There's also a shield terminal. If your cable has a shield, which is recommended, go ahead and connect that here. When routing the serial cable, be sure to keep it as far away from any power lines as possible, especially the ones going to the spindle. Those are super noisy and can really mess up your comms. Well, that's it. Drive's configured, Altmill's configured, and we're now wired and ready to go. All we have to do now is tell the Altmill to use all this. Bring up gSender, go to Config, Spindle Laser, and tell it to use the Modbus VFD we configured. Now before I click on that though, look at the RS485 LEDs on the SLB EXT controller board. They aren't blinking because the Altmill is currently in PWM mode and not using the serial channels. When I select the Modbus VFD, we now see the green LED blinking, which tells us the Altmill is sending periodic commands to the drive, and we see the red LED, which tells us the drive is responding. If I unplug the RS485 cable, we see the green LED blinking, telling us the Altmill is sending commands to the drive, but there's no blinking red LED, which tells us the drive is not replying. Plug the cable back in, and now we do see the red LED blinking, telling us the drive is replying. So if you only see the green LED messages going out to the drive, then the drive isn't replying, and either the RS485 wiring is backwards or something's goofy with the parameters. Try swapping the RS485 wires first, that's easy. Just swap these two wires. If that doesn't get the red LED blinking, switch the wires back and take a close look at the gSender configuration. So always check the RS485 status LEDs when debugging your RS485 setup and make sure both LEDs are blinking. If I set gSender to 7500 RPM and tell it to run in the forward direction and bring up parameter 2 on the drive, yep, we see 7500 RPM, which tells us our input scaling was correct. That's the scaling from the Altmill to the drive. Now just to be sure, go to the max RPM, and the drive says roughly 24,000 RPM. Perfect. Our input scaling is working. To see if the output scaling is working, open up the console and enter a question mark. This is the RPM command sent to the drive, and this is the current spindle speed read from the drive. If these two are the same, then the output scaling is working. Now if the output scaling isn't working, then you'll get an alarm 14 saying the spindle never got to the correct speed. One of the cool things about the CFW320 drive is you can see the commands sent to the drive. Go to parameter 680 and we see a hexadecimal value representing the drive status bits. That's detailed in this table in the manual. Let's reformat that so it's easier to read. We see that the drive is in remote mode, which is controlled by the switch we added in a previous video. We're going in the forward direction, the output is enabled, and the spindle is currently running, and the run command was received. Hit stop, and once the drive stops, we see only the drive's output is enabled in remote mode. Perfect. One more thing. Did you notice that the drive didn't actually get to 24,000 RPM? To do that, just bump the input scaling factor up a bit. I'll add 1/10 to it, apply, and go back and rerun the test. There it is. That was just enough to push us over the quantization threshold. Be careful though, if you go too far and enable that 13th bit, the motor will spin backwards. Well, we're done. Everything's working as expected. Here's a summary of our troubleshooting checklist. Wiring. Check the red and green RS485 status LEDs for activity. Green is signals being sent from the Altmill to the drive. Red is signals sent from the drive to the Altmill. And verify that plus goes to plus and minus goes to minus. Input scaling. Read the speed on the drive's display to verify it got the correct RPM. Output scaling. Use the question mark in the console to see the commanded and the read RPMs. Drive status. Parameter 680 tells you what the drive thinks it was told to do. Perfect speed scaling. You can add a little to the input scaling to move it into the next quantization step to get a perfect speed translation. If you want to learn how to add a drive ready indicator, automate your dust collection so the dust collector comes on whenever the spindle is enabled, how to enable dynamic braking for super fast deceleration times, or how to use the WEG drive for PWM control, then check out these videos. Speaking of videos, Automation Direct has a ton of videos showing you how to use the WEG drives. And I want to encourage you to take a look at the ones that show you how to use the drive management and configuration software. It makes parameter management and drive backup super easy, and it's free. I put a bunch of links to those videos, plus the drives, manuals, software, parts I used in this video, 2D and 3D CAD models of these drives, and a lot more in the description below. Okay, that's enough. Go play with your CNC.